All right, and we're recording. Let's see. Okay, let me know if you can't hear me or if it's hard to see anything going on. All right, so we're going to talk about valence electrons today, Lewis structures, periodic trends, and that's it. I have not posted any materials yet. I will do that, and I'll also do the quiz for both the lecture and the lab. And I apologize for getting that last one out so late, but I made it due, Sunday night or something like that. So you have time to do that. All right. Okay. So let's first start with valence electrons. So last week we talked about the electron configuration. So if we were to look at the electron configuration, say of carbon, I'll just do that. So that's 2p2. So we have 1s2, so this is carbon, 1s2, 2s2, 2p2. Hold on, let me just close these doors. Can you close those doors for me, Kyle?
Yeah.
Thank you.
Are you talking?
Yeah, I'm talking right now. There's people here. Just close the doors. They can see me. I know.
Hear me.
They can hear you, yes. Okay, sorry about that. So this is what carbon looks like. So when we talk about a valence electron, if we haven't said this already, a valence electron is the outermost electrons in an atom. And they're the only ones we care about. Those are the ones that do all the bonding, the losing, the gaining, the sharing, the transferring, and determine the chemical properties. So we only really care about those valence electrons. So when we talk about the outermost electrons, the outermost shell, we talk about the energy levels. So when we look at an electron configuration, we want to find the highest number. So in this case, 2 is the highest number. And we have 2 in the S and 2 in the P for a total of 4 valence electrons total in carbon. And we can do that for any number of atoms. Also on your periodic table, which I would have handy if I were you, it already says all your valence electrons. Now the only thing that I'm going to kind of gloss over is the D block. So we talked about that last week, right? In this D block. Things get a little, I say things get dicey in the D block because there's things that can happen that, like I said, I'm going to kind of gloss over for this semester, just given the situation that we're in. So we won't talk about the valence electrons so much in the D block. For right now, like I said, I'll come back to it a little bit later, but it says 2 valence electrons, and I'll just explain why they all say 2, but they can actually have more that we'll talk about later. So let's just talk about calcium. If we look at calcium, I'm just jumping down over here, we could see that calcium ends with 4s2. So everything else would be the same, right? So we would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? I did that right. When we look for our valence, again, we look for that highest number. And since 4 is our highest number and we have just 2 in the S, we have 2 valence electrons and we're done. Now, if we were going to go on to scandium, which is right after calcium, it would be all that's here, right? All the way through 4s. So scandium, right? We would go, let's just put like ... Or you know what? Actually, let's practice our noble gas configuration. So because scandium is here, we have to back up to the last noble gas, which is argon. So we would do square brackets argon, and then we would continue on with 4s2. And then remember, when we enter the D, we're always 1 less, 3d1, okay? So, let me just, 3 people are waiting, hold on. Sorry about that, guys. I had to do this waiting room thing. I just admitted some people in. Okay, so, and this will be videotaped. You just missed a couple minutes in the beginning. Scandium, right, argon plus 4s2, 3d1, our valence electrons are still the highest energy level possible. And even though 3 fills after 4, 4 is still your outer shell, your highest energy level. So we still only have 2 valence electrons. And that's why every single element in the D block is labeled as 2 valence electrons because here's 4s, but then it's 3d. Here's 5s, but then it's 4d. Here's 6s, but then it's 5d. So the d block is always one less, so the valence electrons are always in this s, this, you know, either 4s, 5s, 6s, and they're always 2. So every single d block element looks similar to this, right? It has 2 in the s, and then it has a certain number in the d, but the d block is always one less, so the valence shell is always that. So that's why, like I said, the d block is labeled with 2 valence electrons, but other things can happen. So when we talk about charges and, when are we talking about that? Maybe we'll talk a little bit about it next week. It can do some other things that would be indicative of it having a different number of valence electrons than 2. But for right now, we're just going to say they have 2 because of that. So we could continue on and do that for any element here, but you quickly just have this all on the top of your periodic table. So wherever it says 2 val, 3 val, you know, 1 val, etc., it's talking about its valence electrons. And this is how you would graphically see how many valence electrons that you have. That's where it comes from, okay? So we need to represent these valence electrons in a way that's going to show how these things bond. So before I erase this, I'll leave this up so I can draw these Lewis structures. Now this is just the Lewis electron dot of just a single element, and then in a little while we're going to talk about a molecule. So what a Lewis dot structure shows is the valence electrons, and we represent them by dots or X's or lines. So in a Lewis dot structure, so Lewis dot shows your valence electrons. We use the element symbol. So let's just say, we'll talk about carbon. You put the element symbol there, and you imagine that there are 4 quadrants around the element. So 1, 2, 3, 4. And what you're going to do is place 1 electron in each one of those quadrants until you've placed 4. And then and only then you pair up in the same one. Sort of like what we talked about last week with Hund's rule, where you only want to pair when you have to. That's kind of what we're doing now. So we have four beds, right? And we're going to put 1 electron in each bed until we have all beds filled, and then we will pair. So if we were doing this for carbon, we would write the symbol for carbon, and we would look how many valence electrons, 4. So we would put, now I like just to put dots, 1, 2, 3, 4. And that would be the electron dot of carbon, showing 4 valence electrons. If we were to do calcium, right, calcium has 2 valence electrons. And it does not matter where you put them, as long as you don't put them together when you don't have to put them together yet. So you could put them top and bottom, side and side, you know, up and whatever, like 12 and 3 o'clock, it doesn't matter as long as they're not together. So that would be calcium. And then any of our transition metals, our D block elements, again, it would look exactly like calcium, right? It would just be this, but we're not going to be drawing Lewis dot structures for those anyway. So that would be that. Now, so let's do a couple more examples. Let me get rid of all this. And let's just start from the beginning. Let's say we had hydrogen. Well, hydrogen is going to be H, and it has 1 valence electron, and we have 1 dot. And guess what? Everybody in group 1 all end with something S1. So hydrogen is 1s1, lithium is 2s1, sodium is 3s1. So the highest level, or the highest number, is, hold on, I gotta admit somebody. The highest number is 1. The highest number is this S block, and there's 1 electron in there. So everybody under hydrogen is gonna look exactly like this with 1 dot. So we could really write this. We could really just write like the number 1, and we'd have a dot above it, because everybody in group 1, whether it's hydrogen all the way down to francium, they all end with something S1. So they have 1 valence electron, they would have 1 dot. Everybody in group 2, so I'll just use beryllium as my example, right? This looks just like the calcium that we just did with 2 dots. So therefore, everybody in group 2, again, is going to look like that. And it doesn't matter where you put those dots as long as you don't put them together. Now, if you notice on your periodic table, we have 1 and 2, and then it continues on with 3, 4, 5, but underneath the 3 is a Roman numeral 3 with a B, whereas under 2 is a Roman numeral 2 with an A. And then if we go over to group number 13, right, which starts boron, aluminum, gallium, you'll see underneath is 3A. So that the A's correspond and the B's correspond. So the B's always are talking about again, the D block elements, and the A's are kind of like what we call the representative elements, the elements we use more that follow the rules better. So group 13 is sort of like group 3. So a lot of times when I talk about it, I'll just say group 3, meaning aluminum's group, a boron's group, 3A, because that corresponds to that, okay? So I will use 13 just so we are on the same page, but I'll explain why I'm saying that in a second. So here we have boron or aluminum, and now we have 3 valence electrons. 1, 2, 3. Now, why I like to call it 3 is because that's how many valence electrons it has. So if we look here, even though it says group 13, if we cover that 1 of the 13, we have 3 and 3 valence electrons. The same happens with carbon's group. It's 14. If you cover the 1, it's 4 valence electrons. It's also called 4A. So that's why I refer to them like that sometimes. So again, we can write group 3 referring to 3A, and everybody in group 3 is going to look exactly like that, right? So that's boron, aluminum, gallium, indium, and so on and so forth. Then we go over, and now we're in group 14 or 4A, carbon's group. And we did that one already. We have 4 dots. So everybody, again, and you can write 13 if that makes it easier for you, is going to look like that, 1 in each quadrant. Then we go on and we have nitrogen's group, so 15. So here's the first time that we're going to actually have to put 2 electrons together. So it'd be 1, 2, 3, 4, and then we'd have to pair up to 5. So we're group 15, 5 valence electrons. Again, we can cover that 1 or just look at it as group 5A. When 2 electrons are together, and some people don't like this, I happen to like it because I hate writing a bunch of dots. When you have 2 electrons together, you could put them as a line. And the other reason why I like to use the line is because those electrons, when they are paired up together like they are in nitrogen, they don't interact the same way these what I'll call lonely electrons do. So even though these electrons can bond, and we'll talk about that later, it's a different type of bonding, and it's not as normal to see those bond than it is with the ones that are kind of by themselves. So again, I'll write a 5 here, and we'll have a line and 3 dots. All right, then moving on, we have oxygen, which is group 16 or 16A. Now, again, the same thing's going to happen here. We're going to have to pair twice. So I'm just going to write 2 lines and 2 dots. Doesn't matter where those go. And everybody in group 16 or 6A looks like that. Then we have fluorine's group, which is called your halogens, by the way. I don't know if we've ever talked about that. But fluorine, chlorine, bromine, iodine, and maybe acetylene. Are they putting those under the halogens? They are. So halogens, also referred to as halides when they have a charge. So here we'll have 3 lines and 1 dot. And everybody in group 17 or 7A will look like that. And then finally, we have our noble gases. And I'm going to leave helium out for a second and talk about that separately. So let's do neon. And neon has that 1 more electron, right? So it will have all 4 lines, and everybody in group 18, or we'll call it group 8, looks like that, except for helium. So helium's a special case. Helium should be next to hydrogen over here because it has 2 valence electrons, but it is over here because it acts like a noble gas. And why it acts like a noble gas is what do noble gases like to do? They like to not bond. They're full, they're complete. If you notice, it's, again, this is just a graphical way to represent it, but it explains why it doesn't want to bond. If you've ever heard of the octet rule, octet means 8. And 8 is what every atom wants to get to. It wants to get to this perfect 8 number of valence electrons. And here, since each line represents 2 electrons, we have 2, 4, 6, 8. So neon is, quote, full and doesn't want to react. Now, the noble gases can be forced to react, but it takes more energy. You kind of have to, you know, force things. It's very happy to be by itself. So the noble gases are known for being unreactive, and you can look at its Lewis structure and see why. Whereas fluorine likes to react or likes to bond one time because it's got that one lonely electron, and we can guess that oxygen would want to bond twice, right? Neon or nitrogen, excuse me, would bond 3, carbon would bond 4. So when we're looking at bonding patterns later on, our Lewis structures can tell us how many times that's going to happen. So where does helium fall on this spectrum? Well, if we look at helium, as opposed to say hydrogen, or you know what, I'm sorry, let's do, we'll do beryllium since that's in group 2. So if we look at beryllium, we have a 1s2, 2s2, yeah, 2s2, right? And then helium would be 1s2 all by itself. Now, beryllium is starting to go into that second energy level. And in the second energy level, remember, we have that 2p that we can fill up. But in the first energy level, all we have is a 1s. We don't have a 1p. So helium, although it only has 2 electrons, those 2 electrons, if we remember back to last week when we were drawing our arrows, right, it looks like this. Those 2 electrons are paired up. Whereas here, these 2 electrons in the 2s, although they're paired up, beryllium has access to that 2p. So this electron can actually move around a little bit more than it would if it was just like this. So these 2 electrons are together in a way. So when we draw helium, although it has 2 valence electrons, and you would think we would draw it like this, with 1 on either side, we actually draw helium with both of them together because those electrons act like they're paired up and they're unreactive like our rest of our noble gases. So good test question is they'll ask you helium, and if you draw it like this, you'd be incorrect. Helium should be drawn like that to show that those 2 electrons are together and do not want to react like beryllium's 2 electrons would want to react. All right. So if you have any questions, let me know. If not, I'm just going to keep plugging along here. So those are Lewis structures of a single atom. All right. So we need to talk about our periodic trends. A periodic trend is why we call the periodic table periodic. Now, I'm going to get a little feminine on you, but females have their period. Why do we call it a period? Because it is periodic, right? It happens every so often, right? Every 28, 30 days, something like that. The periodic table is periodic because it repeats, just like, you know, the moon cycles are periodic. So when we look at a periodic table, there is a periodic trend that happens. Not only did we just talk about the valence electrons, where everybody in group 1 is 1, and then 2, and then we go 3, and then we repeat it going on. That's periodic. We also have trends that happen pretty periodically. Now, it's not a perfect system. There's certain atoms that kind of break the mold, but for the most part, we have a periodic trend. I'm going to be referring up here, right underneath here, to these arrows, this ARENIE stuff up here. So the first thing we're going to talk about is our atomic radius, AR. Okay, so atomic radius. And that is just the size of the atom, just like it sounds. So as we go across the periodic table, and this is what all my crazy arrows mean, as we go across the periodic table, atomic radius decreases. Okay, so that's what that means. So as we go from left to right, our atomic radius goes down. I'm just trying to write this exactly like I have it listed. And then I write an arrow down like this that says AR. So I mean that we go from top to bottom, our atomic radius goes up. So if you have any questions, let me know. If you're not able to understand my arrow stuff here, let me know. And I'm not able to see that chat. I don't think it's making a noise, which is unfortunate. So I'll try to keep checking the chat window. But it'd be great if you just want to say it and chime in. So again, what my arrows mean is when my arrow goes left to right, my atomic radius goes down, which means that if I was going from lithium to fluorine, lithium would be larger and I would fluorine would be smaller as I went across. And then as I went from up to down, say I started with something like hydrogen, and I went to, down to francium, francium would be larger. So let me try to explain this the best way possible. We're limited on time, and normally we'd be sitting here for 3 hours learning this. But I would like you to kind of understand why this is happening. So we have an atom and we have a nucleus that's full of protons, and then we have all these electrons that surround it. So the nucleus is pulling the electrons in. So I use this really horrible example of sheep and me trying to hug them. Okay, so I'm going to draw my little house, right? Here's my little house like this. And what I have is pens, circular pens around my house that contain sheep, right? I know this is very strange, but I feel this analogy works really well. These pens represent the energy levels around a nucleus. So my house is the nucleus with a bunch of protons in it, and neutrons, obviously. And my electrons are the sheep that are in the pens, getting larger and larger in the energy levels around my house. So if I just have sheep inside this first energy level, and I really love sheep, and the more protons I have, the more my love for sheep is. So the more protons in my nucleus means the greater love I have, and the more I just want to hug these sheep in. So if I just have sheep right here in this first pen around my house, and I have a decent love for sheep. I'm lithium. I have I have 3 sheep, and my love for sheep is 3, right? Because I have 3 electrons and 3 protons. So I'm able to hug those sheep in a certain amount because my sheep love is 3, and I have 3 sheep. But as I go from lithium over to fluorine, what am I doing? Am I adding more pens, meaning more energy levels, 1, 2, 3, 4, 5, 6, 7, or am I just adding more sheep and more love? Well, what I'm adding is, because I stayed within that second energy level, I just kept adding sheep to the same energy level, and my love for sheep, I'll put a lot of plus signs here, just got larger and larger. So I became a stronger sheep magnet, and I was able to pull the sheep in. So if I'm able to pull the sheep in, even though there are more sheep, it's not like they're diffusing my power any. They're right here, and I'm able to pull them in. So as I go from lithium to fluorine, I'm adding a bunch of electrons, but I'm adding them right around my nucleus in the same energy level, in that second energy level, right? So I'm pulling them in. What happens to my radius? It gets smaller. But as I go from hydrogen to francium, I'm now, even though my love for sheep is increasing, my magnet, right? If I go from hydrogen having 1 electron to francium having 87, right? That's an extreme, increase in my love for sheep. The only problem is that where do I add those sheep? Well, I keep adding them to pens further and further away from my house. So when I go outside my house and I start hugging sheep in, I'm only gonna be able to hug these in, the ones that are right around my house. And then this sheep is gonna block me being able to pull that sheep in, which is gonna block me being able to pull that sheep in. Now block a little bit, but block it, right? The further away these sheep or these electrons get from the nucleus, the less they feel my attraction, my pull of them in. It's called shielding. So the reason why we go down is because my nucleus is being shielded by all of the electrons that are in the way. So I go outside and I try to hug all the sheep I have, but the sheep that are right around me are the only ones that are really feeling that pull in. Maybe the next ones feel it a little bit, but the ones after that feel it a little less and a little less and a little less. And what happens is those electron sheep are able to float further away from the nucleus because they're not feeling the pull of my protons anymore. And when they float away, what happens to the radius? It gets larger because they're able to float away. So when we talk about this atomic radius, we're talking about from the center of the nucleus all the way out to the outermost electron. Okay, so let's just review these two. As I go from lithium to fluorine, I'm going across a period. So all I'm doing is increasing my magnet, and all of my electrons are getting pulled in tighter. So as I go across a period, anytime I go across a period, I am increasing my nuclear charge, meaning I'm increasing the amount of positive charge in my nucleus, which is then able to pull all those electrons in, making me a smaller atom. Whereas as I go down a period, I'm adding layers and layers in between. I'm adding these energy levels. And what the energy levels are doing is they're shielding the previous, or I'm sorry, the subsequent one from the previous one, or from the nucleus, and those electrons are allowed to float out further, increasing my radius like that. So as I go across, increase nuclear charge. As I go down a period, increase shielding. So that is atomic radius. If anybody has any questions, let me know. Nothing on the chat. Okay. So keep that nuclear charge. Actually, you know what? I'll rewrite that on the top. Okay. So as I go across a period, I have an increase in nuclear charge. Meaning I've increased, if you think about the nucleus as a magnet, right? I'm increasing the strength of that magnet. And you all have played with magnets to where one's like really crappy and barely, you know, sticks to anything, where one's really strong and it almost pulls your hand in. Well, you're just making a stronger magnet. And that happens in any period. I just used the second period as an example. But even if we were in the fifth period, starting with rubidium, and we went all the way over to iodine, we do the same thing. Even though we're in the fifth energy level, we've now become a stronger magnet from rubidium to iodine in that fifth energy level. Okay, and then down a group, we're increasing our shielding. Am I spelling shielding right? I put the I second before. Anyway, I hope that's spelled right. We're increasing shielding, right? It's sheep in the way of sheep in the way of sheep. Okay, so we talked about atomic radius. Now let's talk about electronegativity. So electronegativity, which on your periodic table is abbreviated EN. And what electronegativity is, it's the ability of the atom to pull electrons in, whether they're its own electrons or other atoms' electrons. So ability to pull electrons in, okay? Again, whether they're your electrons of your own, you know, your own atom, or pulling in other electrons. So the trend in electronegativity is as you go from left to right, your electronegativity increases. And as you go from up to down, your electronegativity decreases. Okay? So think back to what we just talked about with pulling sheep in, right? If we look at lithium, lithium is a lot weaker of a magnet than fluorine. So if fluorine is pulling its own electrons in very tightly, right? Very tight around, whereas lithium, you know, floating away a little bit more because lithium's not as strong of a magnet. If fluorine can pull its own electrons in super tight, well, if there's a little electron out here, it can then pull that in really easily as well because it's got a really strong magnet. Now, do I want to talk about that yet? Okay, yes, I do. I want to just briefly state this. If we go back to the Lewis dot structure, right? Here's lithium, here's fluorine, right? And then here's neon, right? So if we look at these three examples of Lewis dot, I said that everybody wants to be the noble gas. Everybody wants to get this octet, this perfect 8 number, this full shell. Well, if we look at lithium versus fluorine, who is super close to being full? Fluorine, right? It's 1 electron away from being this perfect noble gas, right? This full octet. So wouldn't you think that fluorine would want to pull that last electron in as fiercely as it could? I mean, it's able to do that because, again, it has that increased nuclear charge, but it all ties together. It also wants to pull that in really strongly because then it's full. Whereas lithium could really care less, because if there's a little electron floating around, what's that going to do for lithium? Okay, now it has 2. Now it's got to do that 6 more times after that, and that takes a lot of energy. So when we get into bonding and charges and ionic and covalent and all that stuff, we will talk about this more, but that's one of the reasons why. So it also, there's an increased nuclear charge, able to, a stronger magnet, right? You ever have a strong magnet and go near something, it pulls it right up? That's what's happening here, which is making it more electronegative, pulling in electrons, making it more reactive as well. Okay, any questions? Oops, Jordan's trying to get in, admit. Okay, all right, so that's electronegativity. Oh, and I'm sorry, I only did across a period. So as we go from left to right, it increases stronger magnet. Well, as we go from up to down, so again, we'll do lithium to francium. Here's francium, right? This big, giant atom, which by the way, I would assume it's the largest one. If we look at the trend, it would be the largest one. And then we have lithium, which is a lot tighter. So again, here's this little electron walking down the street. Who is going to be more able to pull that electron in? Little lithium that's got its electrons nice and tightly held, or flubbery francium, which is giant and can barely hold its own electrons in? That electron's going to go towards lithium. That's going to have a higher electronegativity. Not that it wants to pull it in, but it can pull it in. It's just more of an ability rather than a desire. I always liken this to like wearing a morph suit, one of those like creepy, like tight spandex suits, versus wearing a like one of those blow up sumo wrestler costumes. If I wanted to go grab a marker that I dropped on the floor, it would be a lot easier for me to do that in the morph suit than it would be in the giant sumo wrestler costume. So the bigger you are, right, it's harder for you to then grab that. If we go back to the sheep example, I can't even hold on to my own sheep. My own sheep are drifting out into the pasture, okay? How am I going to be able to pull in other electrons that are floating by, other sheep that are walking by? I'm not going to be able to. I'm barely pulling my own in. So lithium being nice and tightly held, you know, not as much as fluorine that we just talked about, but we're just looking, by the way, we're only ever comparing things either in the same period or in the same group. We could do a little more in depth, but again, I'm not going to worry about that. So from lithium to francium, as we increase that size, we also decrease our electronegativity because of that same reason. We have all this shielding going on, and therefore it's blocking that pull of any other electrons, including its own electrons. All right. All right, so that's electronegativity. Now, let's talk about ionization energy, which I have as IE, ionization energy. And that is the energy required to remove an electron. Oops, make that nicer. Remove an electron. Okay, so our electronegativity, as we go from left to right, or not electronegativity, excuse me, ionization energy increases, and as we go from up to down, our ionization energy decreases. So as you can see, it is the same as the electronegativity trend, and it is opposite the atomic radius. I should have left that one up, but atomic, here, I'll write that here. So as we go left to right, atomic radius decreases, and as we go from up to down, atomic radius increases. So electronegativity and ionization energy go together, and it'll make more sense when I explain this one, and it's opposite atomic radius. Okay, so ionization energy, the energy required to remove that electron. So let's go back to lithium again. Lithium's here, and it's got, you know, a power of what, 3 power, we'll just call it, right? And then we go over here to fluorine, and I'll try to draw this a little smaller, and then we have a power of 7. 3, 4, 5, 6, 7. It's a stronger magnet. So if I try to walk over to fluorine, and pull off one of these electrons, it's going to be a lot harder to pull these electrons off than it is lithium, which only has a power of 3. Again, go back to just holding, you know, magnets. If you have really weak magnets, like just refrigerator magnets, very easy to pull them apart from one another. But if you have really strong, like industrial magnets, you're going to have a really hard time pulling those two apart from each other. That's what's happening here. We're increasing our nuclear charge. We're increasing our magnet. Therefore, for me to be able to walk over and pluck one of these electrons off is going to be really hard, versus here where I don't have that strong of a magnet. Again, let's look at the Lewis dot. For fluorine to lose an electron, again, it is one electron away from being happy full octet. Why would it want to lose that electron? Whereas lithium, if it lost this one electron, its previous shell would be full, which we'll talk about later. So it doesn't mind losing that electron because it actually helps it out. It would have to gain 7 electrons to be full, or just lose 1 and then its previous shell is full. Let me elaborate on that just 1 second. So we have 1s2, 2s1, right? Did I do that right? 2s1, yep. In order for lithium to become full, again, it would have to fill up the rest of the S, and then it would have to fill 6 electrons in the P. So 7 electrons total, because we only have 1. If it just loses that 1 electron, now its previous shell, although only 2 is full for the S, because that's all it has. Like every other energy level has an S and a P, a 2 and a 6, 2 in the S, 6 in the P. That's where we get this magical 8 number from. So here, if it loses that 1 electron, boom, it's now full as far as the first energy level goes. So it wants to do that. Take my electron. It makes me full now. Whereas fluorine doesn't want to lose that electron. It wants to gain it. That's why it has a high electronegativity, the desire to pull in, and a high ionization energy, meaning it's going to take a ton of energy to pull that electron away. Okay, so that's lithium to fluorine. So again, stronger magnet. Now we go lithium to francium. And again, we have this big, giant atom here. And although it has a ton of that nuclear charge, it also has that shielding that we're talking about, which is blocking it. So again, if I have my sheep and that outer ring of my sheep is just wandering away, wouldn't it be easy for somebody just to run over and steal one of my sheep or steal one of my electrons? I barely have a hold of these electrons because they're so far away from the pull of my nucleus. Again, just like get the strongest magnet you can, but hold the other, piece of metal all the way away from it. It's not going to feel that pull, even though it's a really strong magnet, which is what's happening here. So we have all this increased shielding, which makes these electrons in this outer energy level really susceptible to being removed, which, by the way, makes francium super reactive. As we go down, especially if we just talk about this first group here, as we go from lithium to sodium, to potassium, to rubidium, to cesium, and then eventually to francium, you get more reactive. More reactive, those electrons are flying off. That's why if you've ever seen sodium dropped into water, it violently reacts. Well, it gets more violent as you go down. There's actually a really great video if you look about, they're called the alkali metals, and there's this crazy British guy with wild gray hair, and they do almost all of them. Francium has a really short half-life, which means we learned about that. It breaks down really easily. So it's not, we're not able to see that, but they surmise it would be really big. Anyway, from the trend. So the reactivity as you go down a period gets increased because of the fact that these electrons are just flying off like crazy. Okay, so if anybody has any questions about periodic trends, I know I hit that kind of quickly, but that's the periodic trend. So what I would ask you, if you just want to back up a second, I need you to be able to draw Lewis structures. All right, so just how many dots, like we just talked about in the beginning, and when you pair those dots up. I don't care if you use 2 dots or a line, that's up to you. And then I'd want you to be able to tell me who would have the higher electronegativity or ionization energy or larger atomic radius if I gave you 2. And I'll only give you ones that are in the same period or in the same group. I'm not gonna, try to trick you with any like staircase things. And again, if you have any questions, let's go over this now. My little arrow signatures there to explain that. All right. So this covers more, again, let me just check chat, nobody's chatting. Okay. The next part of this covers what the lab would have been about. He goes more into depth and than I'm going to. He does more carbon-based molecules. And I'm just going to stick, or larger carbon-based molecules, I'm going to stick to really simple rules for this, and just get you the basics. So we're now going to draw Lewis structures of molecules. Okay, so I will post, there's a pretty good worksheet that goes through the steps on how to figure out the structure. All right, the rules that I will post, and I'll go over here, they always work. They work 100% of the time. But just using the Lewis structures, like I would say, 80% of the time gets you the right structure. So if it's something simple, you can just base it off of your Lewis structure. And if it's a little more complex, if it has a charge, which we'll go over here, using the rules, again, works 100% of the time. So let's just do methane, CH4, okay? So let me do the rules first. We'll start with the rules. Rule number 1, I'll put it over here, is count valence electrons, okay? So how many valence electrons do we have? So we have 1 carbon, and carbon has 4, and then we have 4 hydrogen at 1 each. So we have a total of 8 valence electrons, okay? So our structure needs to have 8 valence electrons. So number 2 is draw in the central atom. Now, if you read the rules, it's usually the least electronegative atom, but it also works a lot of the time. It's usually the one that's listed first, the one that has, there's only one of. Also, it can never be hydrogen centrally because hydrogen can only bond once, which we'll talk about in a second. So you want something that's able to bond enough times to make things work. All right, so we put in our central atoms. Next, we draw single bonds to outer atoms. Hold on, I gotta yell at my kids. Guys, go in the other room, I can hear you. Okay, now, we're not gonna get into this for the case of methane, but we will. I'll use an example after this that goes over that. We're going to fill the octet of the outer atoms except hydrogen. So I'll just write except. I can't spell today. Not, I'll just write not hydrogen since I don't know what's going on. I'm having a very blonde day. After we fill the octet of the outer atoms, we count. If we do not have the amount that we have, then we add lone pair to the central atom. And all lone pair is, when I drew that line that made the 2 electrons in the Lewis dot, like for nitrogen, that's called a lone pair or a unshared pair. So when we count, if we need more electrons, we'll add a lone pair to the central atom, and then our central atom needs to have an octet on central atom. And if we don't, then we just add double and triple bonds. So I'll just put double and triple bonds. So I'll go through a couple examples and this will make a lot more sense. So for something simple like methane, we count it, right? Obviously carbon's in the center. We're gonna draw single bonds to all 4 hydrogens, okay? And then we're gonna fill the octet, but since we're talking about hydrogen, since hydrogen only has 1 electron, it never has an octet. So we don't fill hydrogen, and now we're just gonna count. So every line that we drew, remember a line represents 2 electrons, we just count 2, 4, 6, 8, and we have 8 and we're done. Okay, so this would be a correct structure. Now, if you were just to look at the Lewis dot of this, right? This is what carbon looks like. It has 4 valence electrons, and then every hydrogen has 1. So you can kind of see what's gonna happen. If every lonely electron, every dot wants to pair up, and we have 4 hydrogens and 1 carbon that wants to bond 4 times, I think it's pretty easy to see that we can just draw these lines and draw our single bonds, and we would be done. Everybody would be happy. Every single electron now has a friend. So like I said, 85–90% of the time, you can just use the Lewis dot like this, but the rules work all the time. So let's do one that is similar to that. but a little different because it's not hydrogen. So this is called carbon tetrafluoride, right? We went over the naming. If we were to follow the rules, we would say 4 valence electrons for carbon, and then we have 7 times 4, so that's 28. So we have 32 valence electrons that we need to account for. Carbon is obviously in the middle because it's first and it's the only single one. We draw single atoms, or single bonds, excuse me, to all of our outer atoms. Now, we're not dealing with hydrogen, so we are going to fill the octet. So what that means is to get 8 around the atoms. So, little side note, when we're counting for an octet, when we have a molecule, let's just talk about this top fluorine. We're going to pretend like both those electrons in that bond are only for fluorine for the time being. Even though we are sharing them with carbon, when we count for an octet, we count them as if they're only for fluorine right now, and then when we count for carbon, we're going to pretend they're just for carbon, even though we are sharing them. So all you're doing for fluorine is you're saying, okay, we already have 2, 4, 6, 8. So we just fill it. So it has that full shell like a noble gas. And we're going to do that for each one of these. So we have totally filled valence. And again, even though we are sharing these 2 electrons in the bond, it counts like it's for the fluorine and it counts like it's for the carbon. We're sort of doubling down here. Now, we filled the octet of the outer atoms. Now we're going to count. Do I have the 32 that I'm supposed to have? Well, if I count just one of these fluorines, 2, 4, 6, 8, and I know there's 4 of those that exist, 4 times 8 gives you 32. So I now have all the electrons that I chose, that I said I was supposed to have. Let's go to the Lewis dot. Again, we have carbon like this, and then we have 4 fluorines, and each fluorine has 3 lines and 1 dot. So does it make sense that we would just do that 4 times? So as you can see, the Lewis, just going from the Lewis dot structure rather than going through all of these rules works really well for that. What, Kyle? Okay, go away. Anyway, don't have kids. That's my lesson for the day. All right, so let's do one where we have to add a lone pair. So we're going to do ammonia, NH3. All right, let's do it with the rules. We have 5 for nitrogen plus 1 times 3 for our hydrogens for a total of 8. We're going to put nitrogen in the middle, and we're going to draw single bonds to each one of the hydrogens, right? So we counted, we put our central atoms, single bonds to the outer atoms. We don't need to fill the octet because we have hydrogen. Now we're going to count. Remember, every line counts for 2 electrons. So 2, 4, 6. Well, crap, we're supposed to have 8. So what do? We count. If you don't have what you need, the only way to add that is to add a lone pair, right? We don't fill the octet, right? Because we don't, if these were fluorines, we would have did exactly what we did before. If they were chlorines or bromines or something like that, we would have filled it. But again, with hydrogen, we don't. But when we count and we don't have what we're supposed to have, now we need to add that in. And the only way to add that in is to add a lone pair to the central atom. You cannot add lone pairs to hydrogen. Hydrogen only ever has 1 electron. It only ever bonds once. So we add that. Now we count again. 2, 4, 6, 8. Now we have our 8 that we were supposed to have. This one would have worked out perfectly as well with that Lewis dot. We have nitrogen, whose Lewis dot looks like that, right? 3 dots. I hope you can see those dots. And 1 line. And then we have 3 hydrogens, right? And we have 1 dot on all of those. So does it not make sense that we're just going to draw 3 lines and we already had the lone pair and we get that same structure? Rules work 100% of the time. Most of the time you can do it with the Lewis dot. And when you do a lot of these, you'll realize which ones you can and can't do the rules with. All right, so we covered now adding the lone pair to the central atom. Let's count for double and triple bonds now. So this is one that if you read through the lab, he kind of goes through this litany of ways to figure it out. And I just think it's easier just to do the rules. He doesn't really go over the rules like I'm going over them now and just kind of tries out a bunch of structures. I just think it makes it a little bit harder. So let's see. I probably should have come up with an example for this, which let me try to think of formaldehyde. Okay, so I'm going to write this a little weird. Okay, this is formaldehyde. You could write it a couple of different ways. You could also write CH2O, but sometimes the hydrogens are just written first like that. All right, so let's count our valence electrons. We have 1 times 2 for the hydrogen, 4 for the carbon, and 6 for the oxygen. So that's 10, 11, 12. All right, now we're going to put our carbon in the middle because there's one of it. Even though there's one oxygen, it's the less electronegative of the two. And how we find that out, by the way, 2 things. At the very bottom of some of the atoms, right, like carbon, you'll see at the bottom it says 2.6. If you look here in this little key, that's the electronegativity. And if we look at oxygen, oxygen has an electronegativity of 3.5. But you also know the trend for electronegativity that we just went over. As we go from left to right, we increase our electronegativity. So from carbon to oxygen, we become more electronegative. So we would use carbon in the center. Now we're just going to connect all of our atoms with single bonds. So I'm going to put the oxygen on top, and I'm going to put the 2 hydrogens. Now, why I'm drawing it like this is obviously because I know what it looks like. It does not have to look exactly like this when you draw it. All right, then we're going to fill the octet of the outer atoms except hydrogen. So again, this has 2, so 4, 6, 8. Now that's filled. I'm going to go ahead and count my atoms that I have. So 2, 4, 6, 8, 10, 12, right? I'm just counting lines as 2. So I have all 12 electrons. Awesome. I don't need to add the lone pair to the central atom. But my final rule is to have an octet on your central atom. So every atom has got to be happy. Now, some atoms are happy with less than an octet, hydrogen being one of them. Hydrogen's fine with what's called a duet because it has 2 once it bonds. Boron, aluminum, there are exceptions to having an octet, but most of the time you're going to have atoms with octets. So when I look at carbon, I count 2, 4, 6. Even though it's sharing it again, I'm going to pretend like all of the electrons are for carbon, and I'm only counting 6. Well, how do I go ahead and make that 8? I can't throw a lone pair in like I did on nitrogen before, because that would get me to 14 electrons. So the only way to increase or to fill the octet of carbon is to use what I already have. And that's where we use step 6. I'm going to take one of the lone pairs off of oxygen, and I'm going to make it into a double bond so that carbon is now happy and oxygen is still happy. So even though those electrons were explicitly on oxygen before, and we're sharing them now, they still count for both the oxygen and the carbon. So when I count for an octet, let's say we're counting for oxygen, even though we're sharing it, 2, 4, 6, 8. 8 electrons. Now let's count for carbon. Again, I'm ignoring the fact that I just used those electrons for oxygen, and I'm saying 2, 4, 6, 8. And obviously for hydrogen, 2 and 2, and we're fine. So everybody is satisfied. All the octets are filled, and hydrogen's fine with its duet. So that's how we use the 6th rule. This also could be drawn from the Lewis structure. If I look at oxygen, it looks like that. It wants to bond twice. And then I look at carbon, and it wants to bond 4 times. And then I have these 2 hydrogen that want to bond once. Well, connect the lines, okay? This is going to look ugly as hell. You just made your structure. I would like you to draw it like that. That looks a lot better. Please don't leave this as the final answer. But that's how you can tell that the oxygen is going to double bond, because all the lonely little single electrons have to get paired up, and that's the only way they can do it, is a double bond and 2 single bonds. But again, the rules always work. All right, so those are the rules. Now, let's see. Let's do one more normal example. I don't know if I want to talk about more exceptions to the octet. Let's look at SO2. I think that works out. Hold on, wait a second. Not SO2. Although I feel like that would work out. Sulfur dioxide. No, don't do sulfur dioxide. That's what we're going to talk about next. Let's do H2 Let's just do H2O. I was going to do H2S and get fancy, but let's just do H2O. This works both ways, but let's do the rules. If we count, I have 1 times 2 electrons for the hydrogen plus the 6 here, so that gives me 8. I draw my oxygen, I single bond to my outer electrons, my outer atoms, excuse me. This is hydrogen, so we don't fill the octet, and we count. 2, 4. Oof, I need to get 4 more electrons. Well, the only way to do that is to add lone pairs to the central atom, and that's what water looks like, and I'm sure you all have seen that. This would have been apparent also from just the Lewis structure. Oxygen looks like that, and hydrogens look like that, and voila, we have the same structure. We're going to talk about the shapes of these atoms and why I'm drawing them certain ways next time. Okay, trying to think of another good example to do for you guys. All right, let's do PF3, okay? Phosphorus trifluoride. Let's just do this from the Lewis, because you guys can always go back and do this later. If I look at phosphorus, it looks exactly like nitrogen, because it's in the same group. So it has that lone pair or unshared pair of electrons at the top, and then it has its 3 lonely electrons. And then we draw our fluorines. Well, each fluorine looks like that. And we have 3 of them. So doesn't it make sense that we're just going to do this 3 times? And we would have found from the rules, right? If we would have done the rules, we would have wound up with that. We would have been short 2 electrons. We would have done that. And then everybody would have been happy after that. So that's PF3, which looks exactly like ammonia from before, NH3, because it bonds exactly like that. All right. So, by the way, when we just counted for an octet, let me just draw that back real fast like that. Remember that when I counted for an octet, I counted these electrons sometimes for fluorine, and when I wanted to count for phosphorus, I counted those for phosphorus, and it didn't matter, I was sharing them. That's counting for an octet. So we can reuse them basically. What we're going to talk about now is called formal charge. And what formal charge is it's the actual electrons that the atom is in charge of, right? So the electrons the atom actually has. Actually, there's a lot more going on in there. And how we look at our formal charge, sorry, this should say formal charge, is we look at the periodic table and say how many electrons is this atom supposed to have and how many is it actually showing. When we look at that, we look at our valence electrons and then we look at our bonding electrons. So we have valence electron versus bonding and lone pair electrons. So I left this up here just because this is a really easy example. If we look at fluorine and we look at the periodic table, fluorine should have 7 electrons, right? So fluorine, 7 valence electrons. Now, when we look at fluorine as it's bonded here to phosphorus, we have 3 lone pairs and 1 pair of bonding electrons. Before, when we counted for an octet, we were like, oh, we're just going to pretend those electrons are for fluorine now, and then we're going to pretend that they're for phosphorus in a second later. They're really not, though. They're being shared. And we're going to pretend that they're shared evenly, and that's for next lecture. But really, it's 1 electron for phosphorus and 1 electron for fluorine. And we're just kind of sharing them. But really, in reality, it only really has 1 each, 1 of those electrons in that bond. So when we look at our atom, we look at how many should it have from the periodic table and how many is it actually showing. Well, it's showing 2, 4, 6 because it has those exclusively on it. Those lone pairs are just on fluorine, 2, 4, 6, and it has 1 of the electrons in the bond. So 2, 4, 6, and 1 is 7. So it's supposed to have 7 electrons, and it is showing 7 electrons. So it has a charge of 0. Doesn't have any more or less electrons than it's supposed to have. So when you count formal charge, you take your valence electrons and you subtract out lone pairs, and then you subtract half of your bonds, the electrons in your bonds. So let's do this for fluorine. We have 7 valence electrons minus 6 electrons in lone pairs minus 1, because we had 1 bond and we only get half of that, for an overall charge of 0. Okay? So let's do phosphorus. And obviously that's true. These are all 0 for the other 2 fluorines because they're bonded exactly the same. Let's do it for phosphorus. Phosphorus should have 5 from the periodic table. So again, I'm just going to cut these bonds in half. How many are we showing? Well, we have 2 in lone pairs, and then we have 1, 2, 3, right? Because we get 1 for each bond, minus 3 for an overall charge of 0. Now, that makes sense because this particular structure does not have an overall charge. Everything is at 0 and it's completely neutral. So let's talk about ones that aren't. So I'm going to be referring to the polyatomics on your periodic table. So if we look at the back, and I'm going to be pulling a couple of these out. So let's do ammonium, NH4, different than ammonia. So we have NH4. So we have this structure, we see it's NH4 plus. Let's talk about drawing the Lewis structure for that, and let's also talk about where this charge comes from. So if we look at ammonia, we have 5 valence electrons. I'm going to start with the rules from nitrogen, plus 1 times 4 for each one of the hydrogens. But I have a positive charge. And the only way to get a positive charge is to lose an electron. And we lost 1 electron, so I'm going to subtract 1. So we had 9, and now we have 8. Okay, so we draw our central atom, which is obviously nitrogen, and we do single bonds to all of our outer atoms, and we don't fill their octet because it's hydrogen, and we count 2, 4, 6, 8. We have all the electrons that we were supposed to have, and our central atom, nitrogen, is happy 2, 4, 6, 8. Because remember, when we count for that octet, we're going to pretend like those electrons are all for nitrogen for the time being, and then we're going to look at hydrogen and say, oh, hydrogen's happy too. Okay, but now we want to find out where this formal charge comes from. Where does this positive charge come from? So again, we look at valence electrons and we subtract out all of the electrons in the lone pairs and half of the electrons in the bonds because we're sharing those, so we only get half of what's in there. Well, for hydrogen, hydrogen should have 1, and it's showing 1, right? Because we just cut that in half. So each one of these hydrogens has a 0 charge. It's completely as it should be. It's supposed to have 1 electron, the periodic table said, and it has 1 electron. But now let's look at nitrogen. Nitrogen should have 5. How many is it showing? Well, I only get 1 electron from each one of these bonds, so I subtract 4 for an overall plus 1. So the nitrogen here is what's actually holding the charge because structurally, it's only showing 4 electrons when it should have 5. So it's as if nitrogen has lost 1 electron. So that is formal charge. It's showing what's actually going on in the actual molecular structure. All right, so that's ammonia. Let's try sulfate. Don't want to go to sulfate yet, because then we're going to talk about, let's do one more before we talk about resonance. So we have cyanide, Cn minus. So we count 4 for carbon, 5 for nitrogen, and then we have a negative charge. So just like the positive charge meant that we lost an electron, the negative charge means that we gained an electron. So we actually add 1 to this for a total of 10. Okay, so we don't have a central atom because there's only 2. So we draw single bonds between the 2, and then we fill the octet. Right, and then we count 2, 4, 6, 8, 10. Oh no, I totally messed up. Hold on. 2, 4, 6, 8, 10. Sorry. This one kind of breaks a lot of rules. So 2, 4, 6, 8, 10. Okay, good. So we're here and we have 10. So we're pretending like carbon's our central atom and we just fill the octet of nitrogen. I guess you could have did it the other way, but nitrogen being more electronegative, I just filled its valence first. So we have 10 electrons, but we're not happy. So let's rearrange this structure because carbon only has 2, 4. So let's go ahead and share one of these bonds here. And let's go ahead and share one of these bonds here. So if we look at it, we now have 2, 4, 6, 8 for carbon and 2, 4, 6, 8 for nitrogen. And I'll just draw this other lone pair over there. It really doesn't matter where you put it, but I'm kind of showing the electrons in the bonds repelling the electrons on the atoms. So we have 10 electrons and we have everybody with 8 and we're great. So where does this negative charge come from? So let's start counting. If we look at nitrogen, nitrogen should have 5 electrons. And what are we showing? 1, 2, 3, right? I only get half of those. So -3 and then minus the 2 there, which gives me a 0 charge there. And then we come over here to carbon and we see carbon has 4, and I'm going to subtract out the 2 from the lone pair minus the 3 here, which gives me a -1 there. So as we are showing this structure right now, carbon has the negative charge. It looks like it's containing one more electron than it should be, right? Given that. Now, I'll tell you now that I drew this, this is not the correct structure. Because again, dealing with electronegativity, the desire to have more electrons, nitrogen is higher than carbon by probably not much, but well, 2.6 and 3.1. So actually a more correct structure would be to have, how would I do that now? I gotta flip, I'm gonna put 2 on here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, and that would be a 2. I can't have a quadruple bond, there's no such thing. That might be the only way to have that structure then, unless I'm brain farting on that one. Let me think about that for a second. I had enough. 2, 4, 6, 8, 10. Did I do that math right? 9, 10, 4, 5. Yeah, okay. 2, 4, 5, 6, 7. Yeah. All right, I'm going to leave it at that structure. I think it has to reside on the carbon. I don't think it works out any other way. But if there was a choice between 2 atoms to put your charge on, it would want to go on the more electronegative one if possible. Okay, so let's talk about, let's go to sulfate. So SO4 with a 2 minus. Okay, so we have sulfur with 6 plus 6 times 4, right? Because there's 6 electrons on each oxygen and there's 4 of them, and then plus 2. So we have 24, 30, 32. Our central atom is going to be our sulfur, single bonds to our outer atoms. We're going to fill their octet. And we're going to count, and if you count, there's actually 32, and we're perfect. Perfect, perfect, perfect. But let's count for formal charge. So if we look at oxygen, should have 6. It's showing 2, 4, 6, 7, right? One of those. So each one of these oxygens is carrying a negative charge as we've drawn it just now. Let's do sulfur. Sulfur should also have 6. It's just like oxygen. It's right underneath it. And it's only showing 1, 2, 3, 4. So this actually has a plus 2 in the center. Now, if we look at these charges, the plus 2 are canceled out by these 2 1 minuses, leaving an overall charge of 2 minus. It actually works out fine, right? Because this is what it's supposed to look like, and it is showing that. Now, just like before we talked about hydrogen only having 1 electron, aluminum actually looks like this, and when it bonds, it only bonds 3 times, 2, 4, 6. They're less than an octet. They're okay with not having the octet, some atoms. Well, some atoms can actually increase their octet. They can have more than an octet, not increase their octet, but they can have what's called more than an octet. Sulfur is one of them. The ones that can do it are ones that are in the 3rd row or below. And why that is the 3rd energy level is the first time that we have a D block. So if you think back to our electron configuration, we had a 2s and a 2p, but we didn't have a 2d. It wasn't until the 3rd energy level that we got to a D block, right? This is our 3d. So even though phosphorus and say sulfur and chlorine don't have electrons in that D energy or that d orbital, they can put electrons in there, and it's like having a spare room that you don't like to use, but you can use when you need to. So if you are in the 3rd energy level or below, and the culprits usually are phosphorus, sulfur, chlorine, and anything really below can do that. They can expand their octet. They can actually have more than 8. So I liken this to if we're all on a hike together and the negative charge is a heavy backpack. Well, are we just going to let oxygen carry that negative charge the whole time? So what we're going to do is we're going to take electrons, and it doesn't matter which one that you take it from, and we're going to toss it in and make a double bond. Now, we've now increased it to 8, and that's going to be okay. What does that do to the charge? The whole reason for doing this, because we have a lot of charge right now. Well, oxygen, if we look at this oxygen, it's supposed to have 6, and it's showing 2, 4, and then 5, 6, 1 for each bond. So this oxygen went from having a -1 charge to now having a 0 charge, which is much better. Even though oxygen is pretty electronegative, it would rather not have a charge than have a charge. So what does that do to our sulfur up here? Well, our sulfur now is supposed to have 6, and it has 1, 2, 3, 4, 5. So now it only has a +1, which is great. It's a lot better to have 1 less charge. Well, guess what? We can do that another time. So sulfur can expand its octet to 12. So it doesn't matter really what oxygen you pull from. I like to just do opposite, but it really doesn't matter because, as we'll learn next week, 3-dimensionally, they're all spaced out evenly. So you might think that putting it here is going to have a repulsion to this double bond more, but like I said, it's actually not a 2-dimensional structure. So once I do that, right, so this had a plus sign before, this is going to go away because now that oxygen has 6. And if we look at sulfur, 1, 2, 3, 4, 5, 6, that now has no charge as well. And we still have our overall 2- charge coming in from there. But we now have a structure where we have a lot less charge. Even though those charges were canceling each other out, there was still a lot of charge going on, a lot of unhappy atoms. And we can spread that charge out, you know, and let everybody do that. Now, any questions on that? Sorry, I haven't checked chat in a while. So that is one of the structures of sulfate. So let me explain why I said there was one. So let me go back to the backpack example. If now we have 2 backpacks, are we just going to make these 2 oxygens carry the backpack for the entire hike? How come these 2 oxygens can't carry the backpack? Well, they can. So what happens is a phenomenon called resonance. And what resonance is the movement of electrons around an atom, and it actually creates a lot of stability. So this, and of course I like to make atoms have traits of people. This oxygen says, hey, why do I have to carry this heavy backpack? I want to double bond with sulfur and lose my charge. So it kicks these electrons in to make a double bond. But sulfur now has as many bonds as it likes to have. So as soon as this oxygen kicks its 2 electrons in to get rid of its electron backpack, these electrons now have to kick out and be a single bond because sulfur can't handle that many. The same thing can happen over here. These electrons can kick in, but it means those electrons are going to kick out. So we can draw what's called another resonance structure. So we have our sulfur in the middle, but this time our double bonds are on either side, our left and right, rather than top and bottom. Okay, so I'm just going to redraw this again. And it doesn't matter where you put the lone pairs. By the way, you'll see me draw them like this, like a little hat. That's just showing the repulsion of electrons. I wouldn't mark you wrong for drawing it like I had it here. It's totally fine, but I will draw it like that just because I'm used to drawing it, showing that. So anyway, here's one resonance structure and here's the other. So I can now put my negative charge on those 2 oxygens. And what happens is this flips back and forth millions of times a second, if not more. I don't even know the exact number. But if you were able to see, you would see this structure and then you would see that structure. And if you were to draw the two double bonds here, then you would have to draw them over there and you can figure out, but those are your two resonance structures. Kyle, cut it out. Sorry, my kid is dancing outside the door. All right, so that's formal charge and that's resonance. So let's do another one of those because I know that's a lot to take in. All right, so let's do nitrate, NO3 minus. Kyle, go in your room now. Don't pull the dog. All right, NO3 minus. So we count, we have 5 electrons for nitrogen, and then we have 6 times 3 plus that -1. So that's 18, 23, 24. All right, nitrogen's in the middle, and oxygen goes on either side. We fill oxygen's octet, and we count, and we have 2, 4, 6, 8 times 3, which gives us 24, which we're totally fine, right? But if we look at this, nitrogen's not happy. 2, 4, 6. It only has 6. But we can't go and add a lone pair because then we would increase to 26. So we've got to share. So I'm just going to share this one. Again, it does not matter which one you share. Now, if we look at this, we have not increased our electron count, but we have made nitrogen happy. 2, 4, 6, 8. So where does that negative charge come from? If we look at this oxygen, should have 6, 2, 4, 5, 6, 0. If we look at this oxygen though, 2, 4, 6, 7, 1 more electron than it should have. Same thing going on over here, 1 more electron. Excuse me 1 sec. Guys, I have to. Leave the dog alone. Sorry about that. My kids are pulling at the dog while I'm trying to talk about resonance structures. All right, so these two oxygens have -1, again, because they're showing 7 instead of 6. Well, that would be a -2. How are we just at a -1? Let's look at the nitrogen. So we have 1, 2, 3, 4. We should have 5. We only have 4. Therefore, we have a +1 here on the nitrogen. Now, unlike sulfur and chlorine and phosphorus, nitrogen is in the second energy level and can't access that d orbital, so it can't expand its octet. I can't throw in an additional electron from oxygen to make that happen. So it's got to stay like this. So this negative and this positive are canceling, and the overall charge would be a -1. But what nitrate can do, that sulfate just did, is resonate. So a third of the time, the double bond's going to be here, and then a third of the time it's going to be here, and a third of the time it's going to be here. So this has 3 resonance structures, right? So these electrons will flip in, and those will flip back out, and then we'll have the double bond down there, right? We can fill in our lone pairs here. And then we could do that again, and this time we draw, where we flip those electrons in, and those flip back out, and now we have our third resonance structure, where the double bond is at 9 o'clock, and all the charges would still apply. So when this flips, by the way, you have your 2 negative charges on the outer, or the left and the right oxygen, still have that positive charge here, and then here you would have the negative charges on those 2 oxygens, and we still have that positive charge on the nitrogen there. So that encompasses our rules, as well as our resonance structures and our formal charge. So where that all comes from. So sometimes, there's some little tricks here and there. I can't think of all of them right now to figure out the actual structures. Sulfur dioxide, for example, we were talking about that one before. That was this one, like, I don't know, for whatever reason, I always have to look that one up, but let's do this one. Let's see if I can do this without looking it up. We have 6 plus 6 times 2, so that's 12, so that's 18. So I have sulfur and I have 2 oxygens. We fill their octet, and then we count 2, 4, 6, 8 times 2, that's 16. So I add the lone pair to get to 18. But if you notice, sulfur is not happy because it only has 2, 4, 6. So one of these will throw its electrons in order to fill the octet. Now sulfur can access that D level because it's in the 3rd energy level. So it could theoretically throw that one in. So let's look at it before we do that. We have a 0 charge here on this oxygen, so I'm just not going to write anything in. And this one has a -1, right? So it's 2, 4, 6, and then 1 for 7. And this sulfur has 2, 3, 4, 5, and it's 1 less than it should be. So it's a positive charge. If it were to throw it in, right, what would we get from that? We get 0 charges there and 2 or 1, 2, 3, 4. We've actually I lost my hat. 1, 2, 3, 4, 5, 6, and that would be a 0 charge. But for some reason, I feel like it can be written both ways. I won't give you anyone like this, but just so you know going forward, this might be too strained with all those bonds being on there. And I feel like this one can resonate and share that charge, and these 2 charges cancel out, right? So I could draw the double bond half the time on this side and half the time on that side. 1, 2, 3, 4, 5, 6. But that does look pretty happy. So this one probably is your best structure, but that's how you would figure out charges. And if you can expand your octet and do things like this and make a structure that has no charge on it, then it makes it a lot better. All right, so those are Lewis structures and polyatomics with resonance. So I'll try to find some videos as well too, so that you can watch some more stuff. But are there any questions now before I let you go? And like I said, I'll throw up some worksheets too on Canvas. No questions? You sure? So make sure you just read through the lab. It says to look up stuff in your textbook, so there's really nothing you can actually do. But like I said, I'll put up a bunch of examples, and if you have any other questions, I can answer them too if you just want to shoot me an email. Don't forget about your project. I forget the due date. I meant to look it up beforehand, but I did post that on the announcements. So make sure you're, looking over your project. And that's it, guys. If there's no questions, I'm going to run. Go yell at my kids more. Good times.
Thank you.
No problem.
Yeah, thanks.
I'll put up a quiz either today or tomorrow.
Okay.
All right, guys. Talk to you.